Hi. So this is the third video in our course on classical physics, and we'll be talking about dynamics today. Uh, we'll be discussing basically Newton's laws, momentum, conservation of momentum, and center of mass. So let's get into it. We'll first start off by defining what is momentum. So momentum of a particle is defined as this is linear momentum that I'm defining, which is p vector. It's defined as m times v vector, where v is the velocity of that particle. Now, this is a very straightforward definition. P is a vector, and this is also a vector. And in a similar manner, you can also define momentum for a system of particles. Momentum for a system of particles. So what you will say is that the total linear momentum of a system of particles is the summation of over I, mi, vi vector. So basically you add up all the linear momentums. And this is not normal addition, this is vector addition, right? So the reason we have defined momentum is because Newton's second law is framed in terms of momentum. So we'll come to Newton's laws, and let's begin our discussion by thinking about Newton's first law. Newton's first law, the statement is fairly simple, and it says that objects tend to continue in a state of constant velocity. Objects continue in a state of constant velocity unless they are acted upon by an external force. Constant velocity unless an external force acts on them. Okay, so what does this really mean? Correct? So this means that basically you cannot change the velocity of an object without any force externally acting on it. So that means velocity actually is a magnitude plus a direction. It's a vector. So a change in direction would also count as a change in velocity, right? So even if a particle goes with the same speed but changes its direction, then that also counts as a change in the velocity. And therefore, some force must have been acting on the particle in order to make it turn like this. Otherwise, it would have continued straight, right? So that is the idea. A deeper significance of this law is that it defines an inertial frame of reference. It defines an inertial frame of reference. So what does an inertial frame of reference mean? Basically, we can say that any reference frame where Newton's first law is valid, is an inertial reference frame. It is an inertial reference frame. So any reference frame where first law doesn't seem to be valid is a non-inertial reference frame. Correct. So basically, an inertial reference frame measures the absolute acceleration. So I'll talk about this here. So if there is any acceleration, reference frame does not possess any acceleration. If there is any acceleration in the frame, that becomes a non-inertial frame. And you cannot apply Newton's laws in a non-inertial frame of reference. So it will give you wrong answer. So for example, let's take an example. You are in a train or something, and you are sitting here, and holding a glass of water, right? Water is there in this, correct? Now, when the train is moving at constant v, if the train moves at constant v, then the level of the water is horizontal. Level of water in the glass remains horizontal. So that is what you would notice normally. If your train was not moving, v was 0, or if it was moving with constant velocity, the water level in the glass remains horizontal. However, when the train accelerates, suppose it was going with a acceleration, then the water level will start to become tilted like this. There is a tilt in the water level and it will be tilted backward, okay, which reflects how much acceleration is happening in the train, okay. So all external observers will notice this acceleration, will notice this change in water level, change in level of water. So that means that everybody is seeing the effect of this acceleration, and everybody can conclude that you have an acceleration. Even if you have an acceleration, even if the person outside is moving, is himself accelerating, no matter what happens, everybody outside, even if they're moving with constant velocity, accelerating, moving with zero velocity, everyone will be able to see that the water level is like this. And everyone can conclude that this frame has an acceleration. So basically, an absolute acceleration exists from a Newtonian perspective. Absolute acceleration exists from a Newtonian perspective. We use that to define what is an inertial frame. From a Newtonian perspective, if a frame is inertial, then there is no acceleration in the frame. If the frame is non-inertial, there is acceleration in the frame. Okay, so if two reference frames are moving with constant velocity with each other, then they will be inertial with respect to each other. They are all inertial frames. As long as you are moving with constant velocity with respect to another inertial frame, you are an inertial frame. So keep these things in mind. These are definitions which establish the context in which Newton's laws work. So Newton's laws do not work if you put yourself in a non-accelerating frame. So for example, I will show you an example of why it does not work or when it does not work. So suppose you are going again in the same train, right? And you see someone standing outside. Suppose this train starts accelerating, right? Train starts accelerating. Now, any passenger inside will observe that this person is accelerating backward, right? Sitting inside, you will see that this person is accelerating backward, but you will not see any force on this person. You will not see any force on this person, on the outside observer. Correct? Because actually there is no force pushing him back. You will just see that there is a mysterious acceleration that this body seems to have without any force being present which is pushing it back. So basically it says that this observation violates Newton's laws, because according to Newton's laws, you cannot accelerate without the presence of an external force. But here it seems like this person is accelerating back without the presence of any external force. This is happening only because you are observing things from the context of a non-inertial frame or an accelerating frame. So you need to understand this very clearly. Now, next thing that we want to discuss is the second law. The second law basically states that the net external force on a particle, which is denoted by the summation of F, is directly proportional to the rate of change of the momentum. Okay, is directly proportional to the rate of change of momentum. Actually, it turns out that it is equal to the rate of change of momentum. So total external force on a particle will be equal to dP by dt. Now, since P is equal to M, you can say M dV by dt. P is equal to mv, so this becomes your typical F is equal to ma equation, right? Where a is the acceleration of the particle, and these are all the forces, all the external forces together on acting on the particle. Correct? So I hope that is clear. When we come to a system of particles, we will change this definition slightly, and this will become a special point, which we will call the center of mass. So we'll come to that derivation right now. For now, just think about this as defining second law for a single particle, right? Third law is also obvious. Third law says that to every action, there is an equal and opposite reaction. So suppose you have a particle here and another particle here. let's say this is M1 and this is M2. If M1 exerts a force of F on M2, then M2 exerts a force equally on F on M1. Thing to notice here is that the forces, the equal and opposite action reaction pairs, are acting on different bodies. So M1 is experiencing one force F, which is from M2, and M2 is experiencing one force F, which is from M1. So actually, both of them should accelerate, right? Both of them will go in opposite directions, right? So this will be accelerating at F by M1 and this will be accelerating at F by M2. So Newton's third law ensures that there are always equal and opposite forces acting between a pair of particles. However, you have to be careful that there are exceptions to this law. So exceptions to the third law, I will give you one example where there is an exception to the third law, and it is called the force due to a magnetic force. So if you have been exposed to a little bit about magnetic force, we can construct a situation when forces are not equal and opposite. So let's say this is the x-axis and this is the y-axis. Okay. Now two positive charges are traveling along the x and y-axis. Okay. So let's say this is traveling along this and this is traveling along this. Correct? Now the force, the magnetic force on the part on this particle, let's say this is charge 1 and this is charge 2. On this particle due to this will be different from the force on this particle due to this. Because force will actually be QV cross B, right? QV cross B. What you will do is you will construct the magnetic field due to this particle moving with some velocity. So it turns out that magnetic field here due to this particle would be due to the speed at which this particle is moving. So if it moves at a certain rate V, it will have a certain current I2 associated with this. And that current will create a magnetic field in this region. That current will create a magnetic field in this region. Similarly, this motion like this will have some V1 speed and it will create a current I1 in this region. And that current will sort of create its own magnetic field. It turns out that the direction of force on Q2 due to Q1's magnetic field, which will be given by F, will be Q2 V2 cross B1, will not be the same, will not be opposite as expected as the direction of force on Q1 due to Q2. So in normal situations, what you would expect is that they would exert equal and opposite forces on each other, right? But it turns out that the direction of forces is not matching. It is not opposite of each other. This is a special case, and you can resolve this problem if you associate a linear momentum with the electromagnetic field. If you associate a linear momentum with the electric field here, then this problem is gone and you don't have to worry about any violation of Newton's third law here. But obviously this is a digression and it is a special case, or you don't need to be aware of this at this stage. It's fine to assume that Newton's third laws almost always work, right? Now, what we will think about is what is the net force on a system of particles and what effect does it have? There is a system of particles and there are net force acting on them, and what effect that does it have on a system of particles? So let's say there are n particles, correct? And we will denote summation of Fi. This means basically net external force on the ith particle, Okay, and we can talk about small Fij to denote the internal force on the ith particle on I due to J. So what am I talking about here? I'm saying, let's say there were multiple particles like this, right? and there were some forces from outside that were acting. This is my system. This is my system. There are 4 particles, 1, 2, 3, 4. And there are 3 external forces, F1, F2, F3. These are the external forces. These are being denoted like this. So net external force on particle number 2 is just F1, because F1 is the only force acting on 2. Net external force on particle number 3 is F2, and on 4 is F3. Now, there is a possibility that there are also internal forces on these, right? So we will call this F41 and this F14, because this is internal force on 4 due to 1. This is internal force on 1 due to 4, right? So what we will say is, if we apply the second law, to any particle, say the ith particle, right? How will we do that? Let's write that equation. So second law to the ith particle. So we have to do sum of all forces on the ith particle. This is all external forces on the ith particle, plus sum of all internal forces, right, on the ith particle due to other particles. So summation over ij such that j is not equal to I. So what does this summation mean? This means basically, if I was fixed, you are taking summation from, say, 1i, 2i. You should write it as I1. We should write it as I comma 1, I comma 1, I comma 2, I comma 3, so on till I comma I minus 1. Then I comma I plus 1, and so on, I comma n. Basically, there are n particles, and every other particle might exert a force on the ith particle. We are just adding up all of those internal forces. So this is all internal forces. So the sum of the external forces plus the internal forces should give you the total force on the particle, and that should be equal to dpi by dt, right? This is the momentum of the ith particle. Now, if we do a sum over all particles here, at this stage, if I do a summation, this is just one equation, right? This is equation of motion for one particle. I can write n equations like this, right? So if I do a sum over all particles, I will get this expression, summation of f I, and summation of basically I goes from 1 to capital N, plus summation of ij, I not equal to j, f of ij, correct? And is equal to d by dt of summation of I is equal to 1 to n p of I. So what I'm saying is, I add up all the external forces, I add up all the internal forces, and that should be equal to the rate of change of momentum of all of the particles, right? It will be dp1 by dt plus dp2 by dt and so on. So that is what I'm writing, d by dt of p1 plus p2 plus pn, right? Now notice here that this term will immediately cancel out. This term will immediately cancel out, because you know that f of ij is equal to minus fji, right? And both these terms will appear in the equation, right? Because one time you will count the force on I due to j, and later when you write the j equation, you will count the force on j due to I. Those pairs will cancel and this becomes 0. So what you end up getting is total sum of external forces is equal to dp by dt, which is equal to summation of I goes from 1 to n of mi dvi by dt, correct? So this is for all the particles that we are doing, right? So this becomes summation I goes from 1 to n mi dai by dt, right? Correct. Now, here, once we get this, now we can define something called a center of mass. because now we will see if we define center of mass of a system as the coordinate I is equal to 1 to n mi ri by total mass summation of I for mi. If we define center of mass like this, what we can say is that summation of mi r is equal to summation of I goes from 1 to n mi ri, and differentiating this two times, we will get summation of mi d square r by dt square is equal to summation of I goes from 1 to n mi d square ri by dt square. Correct? Okay, I have made a mistake here. I think I should not have written this. I should have written just ai, obviously, because this is dvi by dt, right? So that is just acceleration. Correct. So we get this, which is equal to summation of I goes from 1 to n mi ai. Now notice that this is the same thing as this. And what we can say is this term is called summation of mi and a of center of mass, right? Because r, this was the rcm basically. This was the position vector of the center of mass. And now you have differentiated position vector of center of mass two times. So you'll get macm. So what we get eventually is summation of F external on a system is equal to total mass into ACM. So this is a very important law, because as a consequence of this, we can derive the principle of conservation of momentum, right? So first we defined center of mass. We defined some center of mass as weighted average of the position vectors of each of the particles. Think about this. This is like a weighted average, right? Weighted average of positions of each particle, with the weights being the masses of the particle. Mass is the weight, right? So once you define this, you can define VCM as simply derivative of this. So it will be mi vi by summation of mi, and ACM as this. And we have concluded the total external force on the system. Total external force on the system is going to be equal to total mass, which is the sum of all the masses multiplied by ACM. This has direct implications that if external forces sum is equal to 0, then ACM becomes equal to 0, and ACM equal to 0 implies that VCM will be constant, because ACM is d VCM by dt. So VCM becomes constant. So that immediately means that you have constant velocity of center of mass. And look at this center of mass definition. That means you can multiply this here and say summation of mi VCM is equal to summation of mi vi. And if VCM is constant, then this whole left hand side is constant, because it is just m into VCM, right, is equal to constant. And if the left hand side is constant, now you are getting each of summation of all the momentums is constant. So basically we can say summation of pi is equal to constant. And that has happened only when the external force on the system was not there. If there is no external force on the system, then the momentums sum up to be constant. So we can write P1 plus P2 plus P3 vectors till Pn, and all of it should add up to a constant value. So this principle is very powerful and will help us solve many problems. But before we can do that, we will be able to, we will need to basically find the location of center of mass for many things. So many distributions you will encounter, especially in standard books like HCV, you should check out the derivations for center of mass of a system of particles. Center of mass for continuous distribution of masses. Continuous distribution of masses. So I will give you a couple of examples quickly so that you are used to the idea of calculation of center of mass. So let's take a ring, a half ring, right? The half ring, let's say, has mass m and radius r. And what we want to find out is the location of the center of mass for this half ring, right? So how do we do that? What we can say is, let's take a small element here. We first put our x-axis and y-axis using origin as the center of this ring, and this is my y-axis, this is my x-axis, and we take a small element here. This small element will have length of r into d theta, because this angle is theta, and the basically situation is this: you make one angle theta and rotate it by a tiny amount called d theta. So this total angle is becoming theta plus d theta. So the angle in this portion is simply d theta. Therefore, arc length here will be r d theta. And if r d theta is your arc length, the total mass in that section dm would be equal to m by pi r, because pi r was the total circumference of this half ring. So this expression, basically m by pi r, is your linear mass density here. Linear mass density. So once you have a linear mass density, you multiply it by the small length that we are talking about, so r d theta. So what you get is m by pi d theta becomes your dm. M by pi d theta becomes your dm. Now, if we know that the dm mass is located at this point, dm is at what point? It is at r cos theta, comma r sin theta, correct? So we have to find the location of your center of mass, right? So that should be just simply mi ri by summation of mi, right? But in this case, the number of terms is not finite. We have how many such small elements? We have infinite such small elements, right? Because this dm is very small, or dr, d theta is really small. So instead of a summation, now it becomes an integral. The integral is basically 1 by total mass integral of r dm. This is what you have to do to find the location of center of mass. So let's try to do that integral. It will be basically r vector can be written as r cos theta I cap plus r sin theta j cap. So you have 1 by m integral of r cos theta I cap plus r sin theta j cap, and your dm is becoming m by pi d theta. So m will cancel here, and your theta will vary, and 1 by pi will come out. So it will be 1 by pi outside, and theta will vary from this angle is 0 to when it is this side it is pi. So 0 to pi. So we are getting 1 by pi integral 0 to pi r cos theta I cap plus r sin theta j cap. Now r cos theta integral will be sin theta, but sin theta under these limits will be 0. So this integral will vanish, but this integral will no longer vanish, and it will be minus cos theta, and minus cos theta limits under 0 to pi would be 1 minus 1, right? So 1 plus 1, so it will be 2, and r will come out, and eventually you get 0 I cap plus 2r by pi j cap as your RCM. So this is a fairly standard way to find center of masses. You can see further examples in your HCV where he does center of mass for a plate as well. For a plate which is full, you will get 4r by 3 pi coming as the center of mass. We will see more such problems in the coming classes. What we'll also start doing is applying Newton's laws to solve momentum problems, and also using the principle of conservation of momentum that we saw to solve many other mechanics problems. So what I will show you is some tricks on calculating center of mass in the next video, and also some problems on mechanics which utilize these ideas. So see you next time. I hope you learned something from this video.